When we talk about diseases, one of the principal things we refer to is its basic reproductive number, or in mathematical terms, its R naught. This number represents how infectious the disease is. The higher the number, the easier it is to spread from person to person. With the seasonal flu, we have an R naught of about 1.3. With a virus that causes COVID-19, its R naught is a little over 2. And we actually still don't know the exact number, but I'll use this estimate as a baseline. And while these two numbers may not seem that different right now, as we'll see, they can make a pretty big difference. But first, let's do a visual example of something with an R naught of exactly 2. What this means is someone with this disease with an R naught of 2, on average, is likely to spread it to 2 other people. And those 2 people are likely to spread it to 2 other people. And so on. If we count up the number of people who are sick in each of these rounds, it starts with the first individual, and then we have 3 people sick, and then we have 7 people sick, and then we have 15. And at first glance there, you might be able to recognize a pattern, but if I were to add 1 to all of these numbers, you would recognize a pattern much more quickly. 2, 4, 8, 16. Each of these numbers is doubling, which is what the R naught of 2 is doing. It's doubling the number of people being sick at every round. So let's go ahead and get into the math of how this would work. What I need is an equation that expresses this idea that I'm multiplying by 2 again and again and again. So I'm multiplying 2, and then by each stage I'm multiplying by 2 again, and then by 2 again, and by 2 again. And the mathematical thing that I have to express multiplication multiple times is an exponent. But instead of raising it to a certain number, I'm going to raise it to a variable because I want to know what will happen over time as this disease progresses. So 2 to the x. And because when we wanted to find this sequence of multiplication 2, 4, 8, 16, we had to add 1. In this model, I'm going to go ahead and subtract 1 to sort of take that out. And as you can see, it quickly gets out of hand. It does not take very many rounds of this spread of this infection. In fact, it's only by round 10 that we see that over 1,000 people have been infected from that first person. Well, let's go ahead and take a look at this same thing, but look at it from the perspective of the seasonal flu. Same exact equation. And what you can see here is that they both ramp up, but this one much later, much later. By the time we're at round 20 on the blue graph, we have 189 infected persons. And by the time we're in the same place on the red curve, I mean, we're getting close to 1 million. So the difference between 200 affected persons and nearly 1 million infected persons is the difference between a healthcare system that has no problem keeping up and a healthcare system that's been buckled to its knees with demand. And this is why we've taken the precautions that we have. But as you might quickly notice, this is obviously overly simplistic. Eventually, the disease stops spreading. And the idea is that this R naught will actually reduce the more people are exposed to it, because the more percentage of people who have been exposed to this, the less people there are still to infect, and the rate slows down. So it just doesn't just keep ramping up forever. For the sake of simplicity for this model, I'm going to go ahead and use a population size of 100,000, which is way fewer than the people on planet Earth, but will work great for this graph. I'm going to take my R naught and multiply it by the percentage of people who have not been infected. And what I need to multiply my R naught by is a percentage. So percentage is always out of a total, and our total number of people is 100,000. So that's the bottom of our denominator. The top is going to be how many people are not yet infected, which is 100,000, the total number of people, minus the number of people who have been infected. Well, which variable here represents that? And that is actually what y is representing. So I'm going to actually have y on both sides of the equation. And now when I do this, I see the growth to start to come up, and then as more and more people get infected, it starts to level off, and you can see way below the 100,000 threshold, it becomes more manageable again. And this right here is a perfect example of why vaccination is so powerful. If we can get a number of people immune to a disease, then its ability to spread throughout the community becomes much, much reduced. Okay, even with all those complexities, this is a gross oversimplification of the actual problem. When people get sick, there isn't this total randomness to it. It happens in these clusters where people are connected, and it is much more complex than this model. But this will give you a sense of exactly what mathematicians start to do when they start to think about how to model and think about things like a pandemic.